Welcome to the first part of week 6 of the class Neuronal Dynamics. Last week we have seen that spike timing is variable. If you repeat the same stimulus several times while recording from a neuron, you will find different spike times between one trial and the next. This week we'll continue our discussion of noise models, and we'll encounter the powerful mathematical tool of stochastic point processes. So as we have seen, there are intrinsic noise sources that contribute to the variability. Ion channels open and close stochastically. There's a finite number of ion channels working at finite temperature. This is something like an intrinsic noise source. And indeed, you can follow the stochastic opening and closing of ion channels if you do patch recordings from a piece of membrane. So there is stochasticity reflected in the spontaneous opening and closing of ion channels. And this is a first noise source. However, the importance of this noise source is limited compared to another noise source. From the point of view of the single neuron from which we record, spike timing looks stochastic. It's out of the control of the experimentalist. While the stimulus applied is always the same, spike arrivals caused by spiking from other neurons is beyond the control. And this contributes to the variability of neuronal outputs. The question I will ask this week is, what kind of descriptions can we use to describe these fluctuations, to describe variability in spike timing? What are noise models? Now, last week we have seen a first noise model related to stochastic spike arrival. Suppose you have a leaky indigo fire neuron. It's essentially a passive membrane. Now, if you have a deterministic part of the stimulus, then integration of this equation will give a noise-free trajectory. However, since there are also stochastic contributions described here by a noise term, the actual trajectory is different from the noise-free trajectory. An actual trajectory is different between one trial and the next. It shows fluctuations, and overall it stays fairly close to the reference trajectory, to the deterministic trajectory. It stays sort of in some tube around the reference trajectory, but the exact spike timings vary between one trial and the next. So this is a first noise model. I call this diffusive noise because this noise term here leads to sort of a diffusion of the actual trajectory away from the noise-free reference trajectory. So that's a first noise model. Now, we can take a completely different point of view. Let's just focus on our deterministic trajectory. The trajectory I would get if I just used the deterministic part of the input, the part of the input that's controlled by the experimentalist, that's repeatable between one trial and the next. And now I add noise in a completely different way. I say, well, despite the fact that the membrane potential has not yet reached the threshold theta, there is already a probability to escape across the threshold. And this instantaneous rate of escaping across the threshold depends on the momentary difference between the membrane potential at time t and the threshold. So this is the stochastic intensity, the instantaneous rate of firing a spike. Spikes are formal events There are points in time. And so overall, this is the stochastic intensity of a point process. Let's call this instantaneous intensity of firing the escape rate, the probability to escape across the threshold. Now, this is the noise model we will discuss now. Later this week, I will discuss the relation between the two different noise models. But let's focus on escape noise now. So here again, the basic idea. I can construct a deterministic trajectory, for example, in a leaky integrated fire model, by looking at the deterministic part of the input. This gives me a trajectory. And then I say, well, even though the trajectory hasn't reached the firing threshold yet, there's already an instantaneous escape rate, the escape across the threshold, leading to a rate of momentary spike firing. Even though the deterministic part of the trajectory hasn't reached the threshold yet. But there could also be an instance that I continue to integrate deterministically and I even cross the threshold. And despite the fact that the deterministic trajectory has crossed the threshold, no firing takes place. So this stochastic intensity or escape rate will depend on the difference between the momentary value of the membrane potential and the threshold. And as the membrane potential U approaches the threshold, this instantaneous escape rate increases. While it's below threshold, there's a small rate of firing. If it's above threshold, this escape rate grows rapidly. One possibility is to say, well, the escape rate is an exponential function of u minus theta. And this parameter delta here would control the steepness. If I decrease delta, then it becomes steeper and steeper. So here is our first example of a stochastic intensity. We could have an exponential dependence upon u minus theta. A slightly different, simpler version would be to say this escape rate is proportional to u over theta whenever u is larger than theta. So at u equals theta, I have 1 minus 1, I have 0. If u is larger than theta, I have a positive contribution. And it's 0 for u smaller than theta. And this rho 0 is a constant parameter. So this function is piecewise linear. It would look something like this. Now, if I change the rho 0, if I increase rho 0, then I change the steepness of this increase. And as rho 0 gets bigger and bigger, I get a sharper and sharper increase. So that basically the escape rate is close to 0 as long as we stay below threshold. And then it's very, very big if we are above threshold, if the membrane potential is larger than theta. And this very big escape rate essentially means that as soon as the membrane potential crosses the threshold, a spike is initiated. So the rapid increase corresponds to a rapid response as soon as the membrane potential crosses the threshold. Let me explain this with this additional example. Suppose I have my leaky integrated fire model with a leaky integrator for the subthreshold part, and I apply a current, which is 0, except at this moment in time, where I give a short current pulse. Okay? So if I integrate this, then essentially I have a constant value of the membrane potential. The membrane potential sits at U rest, and then it jumps up to a new value, which I call U0. Now, this momentary escape rate is then a constant. So if this is U0, then this would be rho of U0, and that's a constant. So this means after the switch, the neuron has a constant rate of firing. So this is just like in the homogeneous Poisson process. We now ask, what's the probability to have a first spike here? Well, it's a certain probability. What's the probability to have a first spike there? It's another probability. This probability of firing a spike, a first spike, will decrease over time just because if the neuron has fired here, in the first bin, it can no longer fire its first spike a little bit later. And the mean waiting time would be the mean of this waiting time distribution. So the mean waiting time for this exponential distribution would be just 1 over rho of U0. Now let's look at a different input. Again, it's a short current pulse, but I make the current pulse twice as big. So the jump is now twice as large. The jump size is twice as large, and I have a new value, U1. So now I'm up here, U1, and I have a very large instantaneous rate of high stochastic intensity. In this second case, well, the rate is so high that nearly all the spikes will occur here. So the new tau, the mean waiting time, is 1 over rho of U1. Let's call this tau 1. And this tau 1 is much shorter than the earlier tau 0, if I call this tau 0. So the fact that this escape rate increases rapidly, it's not going to saturate, it really increases rapidly. This rapid increase guarantees that the waiting time until spike firing is really short if we are way above threshold. So the mean waiting time goes to 0 for U much larger than theta if this function f of u minus theta goes to infinity. If this function here explodes, then the mean waiting time is very short. Now this means that, as it should be, if I'm way above threshold, I push the membrane potential up above threshold, then spike firing is reliable and it occurs immediately after the threshold crossing. Let me summarize. So I've introduced the notion of the escape rate. The escape rate is a way to describe the stochastic intensity of a point process. We are in the framework of stochastic point processes. Spikes are events, they are points in time, they are created stochastically with a momentary intensity, which depends on the difference between the momentary value of the membrane potential and the threshold. Now, this is a useful tool to describe stochastic spike firing. It will be used throughout this week and next week. And in order for you to get used to this notion, please have a look at the quiz.